Thank you very much for the invitation to the organizer and to Gabriel especially. So as I said, we are going to be talking about oceanic rock waves under this equation. I'm going to divide this talk into two parts. In the first part, I'm going to mostly talk about numerics. So there's a lot of open problems in this research line, as you will see. There's a lot of experimental data as well. There's a lot of numerics, so they can hint us as possible solutions and things that perhaps we could mathematically prove. And I used to leave this part for the end of the talk, but I think it's actually a good idea to bring it forward so that we can discuss it with plenty of time. And then if I have enough time, I will try to present some of the results that we have obtained recently and some of the things that we are working on. Okay. So of course, there's a lot of people working in this topic, and I will not have time to mention all of the results, but I'll do my best to at least talk about a couple of papers that I think are especially interesting in terms of numerics. First, let me define what a rock wave is. So a rock wave is a wave whose amplitude exceeds that, let's just say twice the height of those of the waves around it. Okay, so this is essentially, you divide the ocean into smaller patches of, let's just say a rectangular patch of a certain size. And we look at the average conditions of the sea in that patch. And this is, of course, a flexible definition. We can say twice, we can say 3 times. But when a wave passes a certain threshold, let's say, then we will call it a rock wave or a freak wave. And of course, these are not events that happen often. These are quite rare, in fact, but they do happen. And when they do, of course, they pose a threat for both ships, for platforms, and for other marine systems. So it is actually very important to understand how they form, when they form, and especially interesting would be to try to identify particular conditions in the sea that could later lead, after a certain time, to a rock wave forming. So one of the theories that people work with is that these waves might happen because of nonlinear effects, and in particular focusing effects. And for this reason, they have often been modeled using the nonlinear Schrodinger equation, the cubic focusing nonlinear Schrodinger equation in particular. But today I'm going to discuss a different model. This is based on the work of Farazmand and Sapsis, who in 2017 proposed a model for these waves based on an equation called the Dysthe equation. As I said, I'm not sure I'm pronouncing this right, but this is in honor of a Norwegian mathematician that you can easily find online. This equation is actually derived from the Navier-Stokes equation, and at some stage, we do not use a full dispersion given by this. We just do an asymptotic expansion of this dispersion, and you can truncate this just to approximate the system somehow. If you truncate it at order 3, you end up with a cubic nonlinear Schrodinger equation, which is what I mentioned before. But they found that if you continue this expansion to order 4, then you can improve the model. Okay, and this is what leads to the Dysthe equation that I will present in the next slide. Their work is actually quite interesting because what they do is they divide a big rectangle in the sea into smaller pieces, and on each of these pieces, they consider Gaussian initial data that are localized to these smaller pieces. And then they evolve them according to this equation forward in time. And after some time, they compute the peaks that form in this wave. And a lot of the data that they consider will not lead to any sort of peak, but some of them will. And of course, we're interested in identifying precisely which kind of initial data might lead to this sort of phenomenon. Okay, so here's the equation. So let me perhaps explain a couple of features of the equation. First, you will notice that the variable x and the variable y work very differently. So there's x's all over here, but it's not symmetric in any way if you change x by y. And there's also x in the nonlinearity here. And this is because in the derivation of this particular equation, we choose to do a change of coordinates so that waves are actually propagating in the direction of the variable x. So we have here essentially. And this creates a very anisotropic behavior, of course. I should also mention some other particularities of this equation. So the degree of the linear part is 3, as you can see by this term here. But also we have another term here. And there's going to be quite a lot of interaction between these two okay, guys. So I'll explain more later. And another feature is the nonlinear term of this equation. So here we can see the cubic part from the nonlinear Schrodinger equation for that third order truncation. But there's other terms, like for instance, this one here and this one here. And in fact, this actually is going to create quite a lot of trouble because we find derivatives in the nonlinear terms. So I'll discuss what issues this might bring in a little bit. Because this equation is actually difficult to work with, perhaps I'll simplify the model a little bit and just look at the one-dimensional equation. So imagine we just look at something like this direction x, for instance. And so then we have the one-dimensional Dysthe equation. And this was actually studied a couple of years ago by Dematteis, Grafke and Vanden-Eijnden. And they essentially, so here's the equation that I wrote. You can see that it shares quite a lot of similarities with the previous one. So one of the things, of course, is this third order nonlinear term. And of course, the nonlinear terms are actually very, very similar to the ones that I just presented. And so what Dematteis, Grafke, and Vanden-Eijnden do is they look at initial data that has the form of some Gaussians. So these theta ends that I write here are just Gaussian random variables with mean zero and the covariance structure that I explained here. And they fit the coefficients, these coefficients Cn, are fitted in such a way that the type of initial data they consider ends up matching experimental observations. So in particular, they are taken in such a way that the energy spectrum of the initial data U0 actually matches observations from the joint node C wave observation project, John Swap. Okay, so there's a lot of numerics there, but it's actually quite interesting. And here's what they do then. They fix some height, Z, let's call it. And the goal is to understand this probability. So this is the probability that given some sort of initial data U0, after some fixed time t, the maximum height that we see in this rectangle passes this threshold z that we just created. This is actually a flexible definition, I should say. There's other observables. We could try the supremum in time here. We could try other functions of u. But this is good enough to start with, I think. And it illustrates a little bit the procedure that they have in mind. And so computing this probability, it's not simple. We need to understand a little bit this set omega of initial data that later will lead to a large peak forming. And so even in the finite dimensional case, so one possible approximation to computing this probability would be, well, remember the initial data before, we cut it off at some frequency n, and we don't go further than that. And then what we end up is with the finite dimensional vector of Gaussian random variables, with mean zero and covariance just the identity. And so we can explicitly compute, at least in theory, this probability. All we need to do, of course, is we integrate the density function over this set omega. Okay, unfortunately, this is difficult to do in practice. Theoretically, we also should be careful about this, of course, and one needs to make sense of this as this number n goes to infinity. So again, lots of open problems here. But even computationally, this is very expensive. And so instead, what they do is they follow a slightly different approach. They just try to approximate what this probability is in the tails. And so to do that, they use large deviation theory. I will not go into details, but there's a principle in large deviation theory that tells you that the largest contribution to the probability that I mentioned before actually comes from one particular initial data, U0, here. That is a solution to this optimization problem. So if you minimize over all the possible initial data, you minimize this norm. And this norm, I don't want to get into details, but it's essentially a weighted L2 norm. So you can think about it almost as an L2 norm. And it's weighted by the coefficients Cn that I presented before. And so essentially, if you minimize this and you find the U0 with minimum norm, then the probability of these tails is approximately equal to the exponential of -1/2 times that norm. And this is, of course, asymptotic as z goes to infinity. So what I mean by this is that if you take logarithms on both sides of this equation, then the quotient goes to 1 and z goes to infinity. Okay, so again, another question that I think is quite interesting is, can we make this rigorous? And of course, this is an approximation as z goes to infinity. So there's a question of how soon, what happens with lower z? Like if we fix z of like, I don't know, 5 meters, 8 meters, which is perhaps what would be interesting in for this type of waves, then does this approximation actually work? And we do not have a rigorous mathematical solution to that as far as I know, but we do have numerical experiments. So here's what they do actually. If you look at this graph here, they essentially consider different initial data of the form of Gaussians that I described before. And what they do is they evolve them according to this one-dimensional Dysthe equation. They fix this threshold 4.8 meters of height. And they take snapshots at different times. So this is time 0, this is time 10 minutes, and 20 minutes. And what you see is that, of course, a lot of the initial data that they actually consider will not lead to any sort of large wave forming. But they can do Monte Carlo simulations where they disregard everything that doesn't lead to a large wave, and they only keep that initial data that does. And then you can average among all of those initial data. And so this is precisely what they draw here in this light blue line that we have. So you can see it here. And then they can also use the large deviation principle that I described, even again, as this z number is far from taking it to infinity, just to test whether this could be a reasonable approximation. And so they draw that in black. And you can see that they actually managed to identify, they are actually quite close. As you can see, the error in this approximation, especially in the last snapshots, is actually remarkably low. So it could be interesting to try to make this rigorous, at least to some degree. Perhaps one cannot find a specific U-naught, but get some sort of interval of confidence, or as you can see, there's many open problems. There's also questions that come to mind at this stage. One of them is, does the size of the domain actually matter? And again, we have numerics about this. And in the paper of Dematteis, Grafke and Vanden-Eijnden, they present quite a few. Essentially, the intuition is that if you make the domain large enough, then you will see sooner or later somewhere these events forming. And usually they will happen sooner just because the domain is so large. So somewhere in the domain there will be something. But it'd be interesting again to make this rigorous in any way, and also perhaps try to quantify, even if we are optimistic, whether the size of this domain affects the time that we have to wait, or in what way these two things could interact. So perhaps let me switch gears a little and go back to the two-dimensional equation and tell you what we can do at this stage. So this is, of course, the starting phase of this research line. So instead of looking at the two-dimensional problem on a rectangle, there's many reasons why that's more difficult than the problem in R2. One of them has to do with dispersion. So for those of you who are not so familiar with dispersive equations, dispersion does not work so well in these compact manifolds. Even if, well, it depends on the manifold, of course, but even if we look at the torus and we take periodic boundary conditions, the problem is actually kind of difficult. So we start with a simpler approximation in a way that we hope that perhaps the technique that we use will actually be useful for the more general problem. And so we look at the case of R2, and this equation that I write is essentially the same as before. And so the first question one should ask, that is, as far as I know, it was open, is whether this is actually well posed. Do we have a solution to this problem at all? And this is interesting both because we're trying to make rigorous all the computations that we were discussing before, and this is of course a basic issue, but also because it'll tell us a little bit more information about where the solution might live as the time evolves, of course. And perhaps having this deterministic study can help with the probabilistic one that should come later. So before we go into details, I'd like to discuss perhaps the linear equation, which is slightly easier than the nonlinear one, because thanks to the Fourier transform, we can actually solve this explicitly. So if you take the Fourier transform on both sides of the equation, you will see that it becomes an ordinary differential equation in time, and so you can solve it. And here's the solution. So this is the inverse Fourier transform of what you find after solving a differential equation. And you can see that this in frequency space is just some sort of oscillation. So there's of course conservation of mass and other properties such as that one. And in fact, this also shows an important topic in dispersive equations, which is the fact that in general, you do not expect the solution to this problem to have any more regularity than that of the initial data. Okay, so in fact, if the initial data has one derivative, then what one expects after seeing this is that this is going to oscillate, but you're not going to gain any more than that. Unlike what happens perhaps with something like the heat equation, which creates some sort of regularization. So this shows why the moment we plug in a nonlinear term here, so suppose that instead of 0, now we have n on u for some nonlinearity n, this is going to create quite a lot of trouble, especially if we have many derivatives in this nonlinear term. So one of the techniques to look at this nonlinear problem actually is to weaken the notion of solution. And this is done via the Duhamel formula. So we can essentially propose an equivalent problem to some degree, which is given by the Duhamel formula, as I was saying, by writing it this way in particular. So I'm not going to focus on the constants, but this is the basic idea. And one can essentially check that if you differentiate, if you have enough regularity after solving this problem, this integral equation that I wrote on top, then one can differentiate this integral equation and show that the solution actually solves this other problem pointwise. Okay, but there might be weaker solutions that solve this integral equation that perhaps do not arise a solution of this because we don't have enough regularity. So let me first remind everyone, since I'm not sure what the background is in these talks, let me remind of the notion of solution that we are using, at least in this context of dispersive equations. The idea is that we will say that a problem like the one I presented is locally well-posed in some subvolular space HS. If for any initial data, so suppose that we have some initial data U0 here that lives in a space HS. Again, we expect the solution then to live in the space HS uniformly in time. So this is why we take this as the solution space. So we say that there is a solution and it's locally well-posed when there is some time t, capital T, and some open ball B around this initial data. This is B. Such that, and also a subset of this space X, whatever that might be, so that if we take any other point here in this ball, U0 tilde, then there is a solution to the integral equation here that lives in this space X. And also in such a way that the map that I just described, this map here, is continuous. Okay, so this is all the ingredients that you would expect from the notion of solution of Hadamard, for instance. This has existence, uniqueness, and of course we have some sort of continuous dependence on the initial conditions of the system. So now that we know what a solution is, perhaps let's discuss techniques on how to find one. And one good technique is the contraction mapping principle, which is also known as the Banach fixed point theorem. The idea is that you use the right-hand side of the integral equation to define this function of phi that I have here. And then the problem of solving the equation just becomes one of finding a fixed point of this function of phi. And of course, this is something that we use actually in any basic undergraduate ODE class. And this is where we prove that solutions to ODEs are, exist locally. And the Banach fixed point theorem just allows us, to find conditions under which this fixed point actually exists. So one of the conditions, of course, is that this function of phi must map a space X to itself. And another condition is that it's a contraction. So we want it to be Lipschitz and have Lipschitz constant below 1. In that case, this contraction mapping principle actually gives us a constructive way of finding a solution as the limit of iteratively applying over and over again this function of phi. So the real difficulty here, as compared to what I was discussing in the typical ODE class, is that finding this space X is actually quite difficult in practice. And at least in dispersive theory, as far as I know, there's no universal way of finding this. It's more of an art, if you will. One technique, of course, is one can look at this sequence of functions that I that I have here. And look at the first few iterations of this. So perhaps we look at linear evolution, which could be U0. So bad choice of data. Let me call it U1. And look at the next iteration given by 5. And perhaps if we find a common space where they both lie, then we are at least in good shape to try to prove that this is the reasonable space X. So perhaps let me show one example on how one constructs this space. Or rather, one example of how one doesn't construct this space, at least for now. Here's the KdV equation. So this is an equation that shares a lot of similarities with ours. This is used in practice to model the propagation of long water waves in a channel. And the similarities are quite a lot, actually. The first thing, despite it being the one-dimensional equation, we have that the linear part of the operator actually has degree 3. And we also have that the nonlinear part has one derivative here as well. So there's a lot of the issues that we will see for other equation actually can be understood in this version, in the KdV equation. I should mention also that the KdV is really only the case k equals 1. K equals 2, I think, is called modified KdV, and then generalized KdV from then on. But these are just technicalities. So here's an idea that doesn't work, but I think it's instructive to test. The first thing that we could try is, well, since in the case of the linear problem, the moment the solution lives in the space HS with some regularity S, no matter how large, then we have that the solution to the linear problem is actually in HS for all future times. Then we might have the idea of testing this space precisely. Maybe in the nonlinear problem, we also have this to be a good space. Unfortunately, that is not the case. So if we take the norm in this space in both sides of the integral equation that I presented, you will quickly notice that in order to control the HS norm of phi u, you actually need to control more in terms of the right-hand side. So here, if you want to think about this, you can think about this as the case S equals 1, for instance. And you can tell that the worst term in this nonlinear term is actually going to be when all the derivatives, so there's one term in this, when all the derivatives actually hit the same guy u. And then to control one derivative of the left-hand side, I need 2 derivatives on the right-hand side. So there's no way really that I'm going to be able to close this contraction mapping in this sort of space. Okay, so this phenomenon is actually known as loss of derivatives. And in dispersive equations, it's actually difficult to deal with. So here's one technique that is actually quite useful, and I want to discuss today. Here's the smoothing effect. And there are many versions of the smoothing effect in this particular estimate that I'm showing here. This one estimate comes from the work of Koenig, Ponce, and Vega in the KdV equation precisely in the 90s. But the first version of the smoothing effect was found by Kato in the 80s. And the most interesting thing about the smoothing effect is that it allows us to control one full derivative of the linear term with absolutely no derivatives of the initial data. Okay, and of course, this is not a contradiction. I want to highlight that with what I was mentioning before. We still do not expect the linear flow to have any more regularity than that of the initial data. The reason why this works is because we're first somehow integrating in time. So we're somehow taking this an average in time. This is not a pointwise estimate. In fact, if we had a pointwise estimate, so what I mean by that is if we switch the order of these two spaces, then there's no way this could work. We would very quickly reach a contradiction because unlike the heat equations or some others, these equations are time reversible. So you could somehow iterate this regularity all the way back, propagate it back to the initial data. Okay. But the most important part about this smoothing effect precisely is what it brings to the table in terms of the contraction mapping argument that I was discussing before. So here's the idea. So suppose that instead of the space X that I considered before, now I consider the space X and I also have this norm given by the smoothing effect. Okay. Then the first step in the iteration argument is going to be exactly the same as before. We're going to end up having to control this nonlinearity here. But now we have more tools. So of course, the most important thing is being able to map the space X via phi to itself. So we want to end up controlling the right-hand side of this equation with pretty much the same norms that we have in X. So now not only do we have the norm in HS that we had before, now we also have the smoothing effect norm. In fact, that's pretty much the idea that we used here. So as I said before, for the purpose of this argument, you can imagine that S equals 1. And therefore, the worst term, again, when we're estimating this, is going to be given by the term in which all the derivatives actually fall in the same guy. And so the idea behind the smoothing effect is to try to position this guy in the space given by the smoothing effect. Okay, so the way we do that on a technical level is we just take the Cauchy-Schwarz inequality here, so that we end up with both L2 in space and time. Then we prepare to use the smoothing effect by swapping these spaces. And finally, we use the Hölder inequality to position the bad space in the smoothing effect norm. Okay, and the other function just goes wherever it has to go. So you can see that this is actually a great idea in terms that we end up with the same space here and here. Okay, but unfortunately, another space shows up. So this is not quite an argument that you can close. But the moment we add this space to our estimates and we develop estimates for the linear propagator in this new space, which are called maximal function estimates, we can actually close. And this is precisely what Koenig, Pomp, and Vega did in the 90s. And this is how you show the KdV equation is locally well-posed, or at least one of the ways. So since we have a little bit of time, this is the only proof that I will give in the whole talk. But I think it's, for those who haven't seen it before, I think it's very instructive, and it's a two-liner really, so it's really worth it. How do we prove this smoothing effect? It's actually quite simple. The idea is that here I wrote the linear evolution for the KdV equation. And so we're interested in controlling one derivative of this guy. So this is actually quite simple. All we have to do is we first take the derivative here. So we know that in Fourier space is equivalent to adding a function C here. And all we do is a change of variables. So we call C cube is going to be mu, our new variable. And then what I wrote in equation 1 just becomes here equation 3. Okay. And then we notice this term here. So this really looks like an inverse Fourier transform in time. And therefore, we can actually exploit this. If we take the L2 norm in time precisely, the Planck-Charles inequality tells us that the L2 norm in time of this guy is just going to be the L2 norm in time of the L2 norm, sorry, of whatever is the integral here, which is what I wrote here. So then you undo the change of variables and you end up with just the L2 of the initial data, no derivatives at all. Okay. So one of the things that one notices quickly in this proof is that despite its simplicity, it's actually quite easy to generalize. And this element here, this C cube, which comes from the term with 3 derivatives in the KdV equation, there's nothing particular about it. So one thing that we can do is generalize this for other dispersive relations, phi. The only thing that we need to ask of this is that we can actually perform this change of variables in some way. And so we need to ask that this phi is a C1 function and that it doesn't vanish except perhaps at 1.x0.
Ricardo, you have 3 minutes left, roughly, just to tell you.
Okay, perfect. I should be able to wrap it up. So unfortunately for the Dysthe equation, as I was saying, this function phi does not satisfy this condition. So we would like, since we want to gain back one derivative in x, there's no way we can do that. The equivalent problem would be having this derivative with respect to c not vanishing. Okay, and unfortunately it does vanish in large regions of the space. So one thing one can do is divide the frequency space into smaller pieces in such a way that in each of these pieces, at least one of the derivatives, the partial derivatives of phi, does not vanish. Okay, and in fact that can be done. And here's the kind of result that one can prove when we do that. The idea is, never mind these regions R1, R2. So this corresponds to the first variable, the derivative with respect to the first variable not vanishing, and this is with respect to the second one. Okay, so nothing special about it. And the idea is that you can take then a smooth cutoff, P1 and P2, that corresponds to each of these 2 regions here. And then one can prove a version, an anisotropic version of the smoothing effect on each of these 2 regions of space. The idea being that, of course, I want you to notice that the variables x and y actually work very, very different, both of them. And unfortunately, if we try to run back the argument that we did for the KdV equation, you will see that after the Hölder step, this will lead to more maximal function spaces. In particular, you will end up with quite a few spaces to control. And so something that in KDV is slightly simpler in terms of the amount of spaces that you use. Here you end up, with space X that is form of many, many, many norms. I won't lie to you about that. But on the other hand, this provides a very good control of the solution U, and you know exactly where it lives, and you can quantify in a very precise way. So here's the result that we can prove in the two-dimensional space. This is a joint work with Kurianski and Staffilani. And so we can prove that this equation is well posed in HS for any S larger than 1. Okay. We are hoping that in future works we can move this to the torus at least, and try to understand whether this regularity S is optimal, so that we can perhaps start answering some of the questions that I was talking about before in my talk. So anyway, I think it's a good place to stop. Thank you very much, and I'll be happy to answer any questions.